Now we will start the next session on design and simulation of power converters for solar energy harvesting, part 2. So this session will be handled by Dr. DrAnanthaPadmanabha, BR. Dr. DrAnanthaPadmanabha, BR is an associate professor in the Department of Electrical and Electronics Engineering, National Institute of Engineering, Manandawadi, Mysore. He has an MTech in Power Electronics from BMS College of Engineering, Bangalore, and he did his PhD from SVNIT, Surat, Gujarat. And his area of research was improved power quality converters for battery chargers. He has worked in several industries, and he also involved in the design of power converters for several applications such as lighting, battery charging, standby power supplies for LCD TVs, etc. His primary research interests are in power converter design and control, electric vehicle battery charging, motor drives, power quality improvement and reactive power support for the battery of electric vehicles, nonlinear control and estimation. He is currently working as an associate professor in the Department of Electrical and Electronics Engineering, NIE Mysore. He has published several research papers including IEEE transactions and several international conferences, etc. I welcome you, sir, as a resource person for the FDP on hands-on approach for design and implementation of lab on breadboard, a blended learning. Over to you, sir.
Thanks, Dr. Jaishankar. Thank you very much for introducing me to the participants. So, are you able to see the presentation?
Yes.
Yes, it is visible.
So, good afternoon all. I am here to present the design and simulation of power converters, of course, for the solar harvesting. So, it is a continuation of the topic that we discussed in the forenoon session. And these are some of the topics that I am going to discuss in next 1.5 hour duration. So basically, in the previous session, you have come to know that as far as the solar power harvesting is concerned, there are several power converters that we need to design. If you want to implement a solar power converter, several power converters are required. Out of that, in this particular session, like whatever the theoretical session that we are going to handle in the next 1.5 hour, and also in the afternoon hands-on session, some basic converters we will be discussing so that we can implement the same in the solar power conversion. Today's my presentation includes these many topics. Like basically, I'm going to discuss the implementation of buck and flyback converter, which are very common as far as the solar power systems are concerned. That means how to implement these two in TINA design software. But to discuss, that means to implement that in TINA software, there is a little bit of background that is required, which I'm going to handle now. So initially, I will be discussing the working principle of these two converters, and then I will try to highlight the design aspect of these two converters, and of course, the next is simulation. But the afternoon session will include the building the actual model in TINA software and analyzing the same converters. There are some certain analysis are there, like DC analysis, AC analysis, transient analysis, which you are already familiar with in the past 2 days. So the same thing we will be repeating here, of course, for these two converters, that is buck and flyback converter. In the next 1 hour session, I will be mainly dealing with the working principle, design and simulation. That is the preparation for the simulation. And one more thing what I want to highlight at this point of time, when I say design, I am just want to stress the fact that we are not going to design any converter in detail. We just want to highlight what are the main aspects that we are supposed to focus, especially for the purpose of simulation. So here, let us not concentrate too much on the design aspects. Only we will just fly through these two design, that is converter design and control design. But what I feel is there are many participants here from electronics background. So as far as the control design is concerned, it will be really interesting if I focus a little bit more as far as the control design of these two converters are concerned. What I felt was that if you focus more on the control design, maybe it helps to implement in TINA software. So we will not spend much time on converter design, but we will try to spend relatively more amount of time on the control design. Then once we are done with this, the working principle and the design, then we can go to the actual implementation in TINA software in the afternoon session. Okay. So this is a basic buck converter. As far as the solar power converter is concerned, there will be a PV panel, and we are going to buck it down to a lower value. The voltage which has been stepped down will be once again converted to inverter. Converted the AC output to an inverter. So these aspects have already been highlighted in the previous session. Just I want to stress the fact that this is one of the converter which is used in the solar power panel. Okay. I think there is some participant which has please some noise.
Participants, please mute yourself. Dear participants, please mute yourself. Thank you. So you can continue.
Oh, thanks. So here, this is basically a buck voltage regulator, and there are some waveforms that has been displayed on the screen. Basically, this is just a current waveform, voltage waveform. Then which current and which voltage? In any power converter, we are interested in the current waveform through an inductor, voltage waveform across an inductor, across a capacitor. So these two things you must keep in mind always. Whenever there is a power conversion happening, we are mainly interested in energy storage elements. So power engineers they are very much interested in the current through inductor and voltage across a capacitor. So whenever I say waveforms, these are things that has been displayed. In any standard textbook, if you see, this will be the standard waveforms. So the same thing has been shown here. So let us not go in detail. Whatever the sawtooth waveform that you see is obviously the current through inductor, and the sine looking waveform is the voltage across the capacitor. Okay, and once again this sawtooth waveform, which has got both positive and negative component, is supposed to be the current in the output capacitor. And these waveforms have been drawn keeping in mind two modes of operation. Of course, it is just a very simple simplest configuration is switching on a MOSFET, switching off a MOSFET. So when you switch on a MOSFET, what are the things that is going to happen? And when you switch off a MOSFET, what are the things that you are going to listen? What are the things that is going to happen? these two things, whatever happens, it will be in these two modes only. Okay, so the total entire period has been divided into on period and off period, and we have tried to figure out what will be the shape of the current through an inductor, what will be the voltage across the capacitor in these two different modes. To facilitate writing these waveforms, two equivalent circuits have been drawn. If you just see here, mode 1, mode 2 has been shown here. One during switch on and one during switch off of the MOSFET. That is the main triggering point for any mode change. Okay, and here the same thing, same waveforms have been shown here for your convenience. But here only thing is that please concentrate on the last expression that I have written. Okay, what is that? I have written delta I is equal to something. That means we are interested in what is the ripple content in inductor current waveform. Finally, a power electronic engineer will be interested in the how much is the ripple current through an inductor, which amounts to the accuracy. Okay, of course, it has to handle some DC current, but over and above the DC current, that is average DC current, how much exactly is the ripple that is appearing? That is what it is important for us. So we have got an expression for the delta I. If I go to the next slide, you can see that there is delta V. What is delta V? Nothing but the ripple, voltage ripple that is appearing across the capacitor. So the current ripple through the inductor, voltage ripple across the capacitor, these two are the important waveforms. And you are interested in what are the parameters on which these two depends. Because by manipulating these parameters, obviously we are in a position to control the inductor current ripple and the output voltage ripple, which is supposed to be the important performance parameter of any power converter. Of course, this is just a simple mathematical treatment, like normal writing a differential equation, equating volt-second balance, applying a basic theory of applying volt-second balance. And finally, we are trying to arrive at the delta V and delta I. And you know that the design process is always the reverse of analysis. So the analysis is looking as though we are trying to find out the ripple current to the inductor and voltage across the capacitor. But in practice, the design process is the reverse of analysis. What exactly we are doing? We want to find out the value of L and C, keeping in mind some particular frequency of our choice, some particular duty cycle K. I think I have borrowed it from some textbook where they are given the symbol K. Usually we are accustomed to D as the duty cycle. Here in this particular book we have used K. It is one and the same. So basically there are several parameters which is deciding the inductor current ripple and voltage ripple across the capacitor. Same treatment we are going to do even for the buck boost also. Okay. Why I have taken buck boost? Because in the afternoon session I am going to show you the simulation for the buck converter as well as flyback converter. At this point of time, I want to highlight the fact that the flyback converter is just an isolated version of buck boost regulator. Okay. So theoretically, there is no difference between a buck boost regulator, buck boost converter, and a flyback converter. Both are same. Only thing is, the flyback converter is the isolated version of buck boost converter. That's all. So the same procedure is followed here also, even with buck boost regulator. Like there are two energy storage elements are there, L and C, and there are two modes are there. One during switching on and one during switching off the MOSFET. And we are interested in how the current varies to inductor and how the voltage varies across the capacitor and what is the shape and how we can control the shape. What are the parameters that through which we can control the voltage ripple and current ripple. All these things will subsequently follow. That is what we are interested in. Okay. So we will take the help of once again the same theoretical concept that volt-second balance. We are applying the volt-second balance, or you can say capacitor charge balance, whatever it may be. We will arrive at the same results. So with that, we are able to find out the Once again, the current through the current ripple, see delta I. Once again, I am interested in finding out the delta I, that is the ripple current through the inductor, and the delta VC, the voltage ripple across the capacitor. And I am interested to find out what is the exact value. And by designing, I will take the reverse procedure, and I will try to find out the value of L and C to meet my expectation of the ripple voltage and ripple current. This is the normal procedure that we follow. So I have tried to just highlight these two voltage and current ripple expressions for two converters, buck and buck boost. And the next one is the flyback converter. As I was telling you, that it is just an extension. So whatever I have done on the left side, even though it looks different, it is just the same figure that I had written for buck boost. There is no difference. Okay. So the same thing, but only thing is it has been written in a different way. That's all. So that my interest is to slowly migrate from the non-isolated version to the isolated version. That's all. So what I have done, I have just introduced a transformer in between. Because you know that in many applications, the isolation is very much required, either for the safety reason or for the voltage level matching. Okay, maybe the purpose are different, but there are many occasions we will come across where we need isolated versions. So flyback converter is one such converter. Where we are having an isolated converter, and obviously it is a known fact that it has been derived from the buck boost converter. So it has been written conveniently so that we can get the easy migration from the non-isolated version to the isolated version. That's all. There is no much technical things that are involved. You can see that same thing here. And only one point that I want to highlight here, that the polarity, you can see that dot polarities are opposite in nature. Why I want to bring your attention on this one is that when we will implement this one in the TINA software, the way it has been implemented in the TINA software, it will be interesting to observe. So this is just to bring your attention. You can see that usually in a transformer, what we'll do, the polarities will match. Okay, so you can see the dots appear both at the top or both at the bottom. Basically, it is the dot convention will match for primary and secondary. Whereas in case of the flyback, very interesting to observe that they are not matching. Why? Because even though it looks like a transformer, flyback converter transformer is not a transformer, it is a coupled inductor. So at this point of time, you have to remember the fact that it is a coupled inductor. So we can ask the okay. So again, same thing for the purpose of analysis. Again, during on mode, that means when the MOSFET is kept on, how the equivalent circuit looks like. So the figure A is the circuit which comes into picture when the MOSFET is on, and figure B is the picture when it is when the image which is describing the condition of the circuit during switch off of the MOSFET. Okay, and as you can see that here LM, the magnetizing inductance, is shown here. The magnetizing inductance, which we think we have to reduce it to a larger extent in normal transformers. We want to reduce it to as minimum as possible. That's what we are interested, because we want to minimize the magnetizing current as less as possible. But to our surprise, you can see that flyback transformer basic principle works on the value of the magnetizing inductance. So whenever I say primary inductance, it means magnetizing inductance. So whatever the leakage inductance that is present, if you subtract it from the main self inductance, whatever you get it is magnetizing inductance. That's what we are interested in. So if you have to pick up some component in the TINA software, you have to be very careful that this is what you are trying to pick it up from the shelf, so that if we are using the flyback transformer not as a transformer but as a coupled inductor. So this is once again a point to be observed, where unlike a normal transformer, here the dot conventions are opposite. That is one thing you have to observe. The other thing is that the primary magnetizing inductance, which we usually want to minimize in normal transformer, we want to keep it the value, we have to keep it according to our design value. Suppose if we get some 3.3 billion entries, 5 million entries, so we have to wind the transformer in such a way that we are supposed to get that particular magnetism index. Okay. Then, as far as the turns ratios are concerned, usually in normal transformers, what we will do, we want to have some turns ratio depending upon the voltage rating, secondary, what we want. But here, purely the transformer ratio depends upon the output voltage, how much we want to step down, and also it has to meet the inductance. Usually what happens, as far as our normal transformer is concerned, we are interested in to reduce as far as possible. But here, what is, because we are interested in only the self-inductance part of it. But here it is a little bit different because the total working principle is totally different. The only misleading point is that it looks like a transformer. That is the only thing which we have to keep in mind. Okay. Anyway, just some very briefly, I want to go further in this one. Finally, what we are doing, we are trying to arrive that output voltage by input voltage is equal to D divided by 1 minus T. Okay, this is what usually for a buck boost, but only additional thing which has to be multiplied is the turns ratio of the transformer. So other than that, it is just a buck boost converter. As I was pointing out just about 3-4 slides before, I was saying that it is just an isolated version of the buck boost converter. So here what is happening? Since it is an isolated version, I am just going to multiply it by the turns ratio to get the output voltage. That's all. And what I am to arrive at this one, once again, what I'm doing, I'm just applying the what is that? Volt second balance, energy balance. That's all. One thing is I'm trying to catch hold of a different expression. Previously, I was trying to catch hold of the expression for the voltage across the inductor, or you can see the current through a capacitor. And here I have catch hold of the flux. That's all. Everything is same because in all we are going to apply the Faraday's law only. Finally, the Faraday's law is the law that we are applying behind all these things. So finally, we are going to arrive at this expression. Anyway, this is also just for recapitulating, that's all, because all these things are known to you. Okay. Now, here, once again, finally, what I'm doing, IM hat. What is that IM hat? IM hat is nothing but that means the delta current. That means once again, I'm interested in finding out the ripple current through the inductor. That's what. Same thing. Whatever we followed for buck and buck boost, same thing we are trying to express even here for the flyback converter. What is that? I'm interested in finding out how much is the ripple current through my inductor. Okay. But in addition to that, one more expression I have kept here. That means what? Here, incidentally, the current through the primary of the transformer is also the current through the switch. So here, the working principle is little bit not the working principle. The schema is little bit different, so that we have to focus on a point that the current through the magnetizing inductance is also the current through the switch. Anyway, all these things will be made. It will be clear when we take up the actual simulation. So at this point of time, I just want to highlight the fact that once we design any converter, either buck converter, buck boost converter, flyback converter, you are going to use the principle of design principles, and you will arrive at the values of L and C. Once you arrive at the value of L and C, when you are going to simulate, you will see that what are the expected current waveforms and voltage waveforms, mainly across the capacitor and through the inductor, whether it is matching. That's what we have to know. So the other controlling parameters, obviously the duty cycle, the input voltage, load current. Okay. See here, I don't know whether this slide should I go in detail or not. Actually speaking, for this flyback converter, this particular slide, I feel this is supposed to be very interesting, and also I can say that it is quite different from the non-isolated versions. How is that? See, for example, in the first one, I have shown just an inductor. Okay. Whereas I have shown here a coupled inductor. So the second, third, fourth diagram indicates the coupled inductor with different turns. The second diagram indicates 4:4. That means 1:1. 4 turns in the primary, 4 turns in the secondary. Whereas in the second diagram, it is showing 4 turns and 2 turns in the secondary. That means 2:1. Then 1:2. So there are different transformer turns ratios are there. So I should not use the word transformer. I should say coupled inductor. Okay. Whereas here I have shown only one inductor without any coupling. So here in the second row, third row, fourth row, what is shown? Amperes. That means the current through these inductors. Okay. So the current through the inductor has been shown here. And here you can see that there is a rise in current, there is a fall in current. Why? Because only one circuit is there. There is no coupling. But whereas here you can see that there is a rise in current and a abrupt fall. There is a rise in current, abrupt fall. Why? Because as soon as the current abruptly falls in the primary, somebody has to pick it up. Who will pick it up? The secondary will pick up. Okay. So this slide is basically to convince you that the inductor and coupled inductor are one and the same. Only thing is the current flow will be physically at different places depending upon the time. In one particular time, the current flow is through a particular inductor. In other duration, the current flow through is physically through some other path. But that some other path is nothing but the path which has taken the energy from the same earlier, whatever the energy that has been stored, from the same only it has taken. So the energy is not different, but the only thing is the path is different. Whereas here, the energy is same and the path is also same. That's why you can see the continuity. But whereas you cannot see the continuity here, in coupled inductor, you can see that abrupt fall is there. But whenever it is abrupt fall, wherever it has fallen down, it will exactly at that time it will pick up. Okay. So that is what you mean by a coupled inductor. And based on the turns ratio, you can see that here there is equal current. Okay, you can see there is an equal current. Whereas you can see that there is a little bit reduction. Okay, whereas here you can see that. So in all these things, depending upon the turns ratio, the current values will be different. Okay. These things we can observe in the simulation by measuring the current through the output diode and also the input switch. Anyway, this only to highlight the difference between the inductor and the coupled inductor. Let me quickly go further. Now, here, once we are through with the basic working principle, let us try to focus on the design, the two converters which we are going to handle in the afternoon session, that is the buck converter and the flyback converter, right? As I told you earlier itself, when I say design, let us not focus too much on the power converter design because it becomes a detailed discussion. Altogether, a separate slot is required. But already a design converter is there for a particular output power, for a particular input voltage, for a particular output voltage. Everything is designed. That means we have a design, we have design values. We have the value of L, we have the value of C. Only thing is we are trying to implement that. That's all. That means our interest is more to implement it rather than to design. Okay. But having said that, I just wanted to bring your attention more on the control aspect, because power converter design, if you just refer some standard books, you will come to know how to design L and how to design C. That is the most basic ingredient of any power converter. That you can easily come to a conclusion about the design of L and design of C. But I personally feel that as far as the control system aspects are concerned, it is little bit non-intuitive. What I mean to say is, it is not very obvious why the control systems are required, what is the relationship between the Bode plot that we are going to draw and actual values that we are going to use. That there is a disconnect between the theory and the actual implementation. So I just want to focus more on this control aspect rather than the design of the actual power converter. So actually whenever we say design of any converter, it involves the design of converter and it involves the design of controller. Okay, but as I kept on repeating the same thing, let us focus more on the controller design. Okay, so converter design has already been taken care. So especially the most simplest converter that we are going to handle, like buck and flyback, very few, only two energy storage elements are there. Once the values are known, finish. It is design is complete. Of course, all the design principles had to be taken care. That is altogether a different story. But assuming all these things have been taken care, then we are very much comfortable that we can proceed to the controller design, which is quite involved. Okay, I can say it's quite involved compared to the controller design. Okay, so we'll go to the controller design, having taken care of the converter design. Okay. So whenever I say controller design, the first thing that I want to make you understand is that suppose you take any converter if you take, there is some input, there is some output. Usually we are what we are interested in a particular output. Maybe the output may be a particular voltage value, like I want 10 volts, I want 5 volts, I want 6, some voltage value I want, irrespective of disturbances. Okay. In the similar way, let us say I want a particular current from a converter output. So some converter is there. The converter output is current instead of a voltage output. It's a current output. Maybe in some cases it may be something else. It may be what is that, speed output, torque output. Of course, we are not going in all such things. That's a totally different area. Here, as far as the power converters are concerned, usually you can take it. I mean, as a simplest rule, that usually the power converter output will be a voltage output or it will be a current output. Okay. Having decided the value, well, let us say I want so much value of output voltage from converter. Anyway, we are going to handle buck converter and flyback. Let us take the buck and flyback itself, because that will be very much easy to handle. Instead of talking in general, let us try to focus only on these two, that is buck converter and flyback. So this buck converter, this flyback converter, which we have to use in solar power conversion, will have some value, some particular voltage. The question is that to maintain that particular value of voltage, what are we supposed to do? And where exactly we face the problem? Exactly, if some nothing disturbance is there, we don't have any problem. As long as there is no disturbance, even a fixed duty cycle will cater to your requirements, and the output voltage can altogether be very much sure. You can be very much sure that the output voltage will remain same if you are very confident that there is no disturbance. But unfortunately, the real world is not like that. You can see the disturbance are there. Okay. As far as the buck converter is concerned, you can, in essence, you can say that there are only two disturbances. Okay. To simplify our discussion, at this point of time, we will not think, because it is a very popular disturbances in any power converter design is two disturbances are there. One is input voltage disturbance. You can expect some disturbance in input voltage. You can say, for example, you have a 100 volts to 20 volts power converter. Okay, you can expect the input voltage to vary from 80 to 120, because it's some. Let us say that is a battery, and the battery may get discharged to a certain extent, so the voltage may come down, or it may get overcharged because of some reason. In which case the voltage may go beyond 100 volts, or the voltage may be derived from a control rectifier. I mean, uncontrolled rectifier. So the input voltage itself might be varying. You know that suppose if you observe the voltage from morning to evening, you can see that sometimes the voltage may be as bad as 180 volts, 190 volts AC, and sometimes maybe as high as 265 also. Okay, depending upon the conditions. So what I want to say is that there are obvious disturbances that happens as far as the input of any converters are concerned. Since we are discussing buck converter here, definitely there will be, we can expect these disturbances in the input. Then what is the second disturbance? The second disturbance is the current. That means the load will vary. It's very obvious that there is some load for any power converter. Input is there, and output is there. Output is there means what? Output load is there. That load value will change. Based on the application, the load will change. So the change of load is supposed to be one disturbance, and change of input voltage is supposed to be one disturbance. But here I want to highlight one point. What is that? The change of voltage itself is not a disturbance actually. But then what is the exact disturbance? Because you know, if you change the input voltage, the output voltage has to change according to the topology. If it is a buck topology, output voltage is equal to input voltage into duty cycle. If it is a boost converter, output voltage is equal to input voltage divided by 1 minus D. So it has to follow just the output to input voltage ratio. So what is the question of disturbance? Why we should call that as a disturbance? Similarly, if the current changes, what happens? Let the current change, and the new conditions, whatever that is appearing, and obviously the duty cycle has to change. Why we should call it as disturbance? Basically, whenever we say disturbance, it means that the power converter has to adjust to the new conditions. Okay. Here is the occasion where the word disturbance comes into picture. How? See, whenever the power converter has to adjust to the new conditions. Whenever I say new conditions means what? New current value or new input voltage value. Then we have energy storage elements in any power converter. Without energy storage elements, we cannot even think of any power converter. So these energy storage elements have got inertia. Okay, we can say it is elements which contribute for time. That means it will not respond immediately. Whereas a resistive element will just jump to any change that you dictate. But whereas inductor and capacitor will not do it. If you ask the current to change through inductor now, it will do so after some milliseconds based on the time constant. That means it's an element which is having very reluctance. It will not respond immediately. Just like that, a capacitor, whenever you ask the capacitor voltage to change from one value to other, it will not do so instantaneously. It will take some time. So basically, what are those energy storage elements? They are inertial elements. These inertial elements are the ones that are supposed to be. I mean, they are one which has to be handled properly through the controller. Because the moment you ask to change, since they are not going to change immediately, time is going to get involved. But as soon as the time gets involved in the picture, what happens? The controller, there is a lot of probability for the controller to get confused. Okay. So unlike a human being, it doesn't know whether the correction it is making is because of its own making or it's because of the external disturbance. That kind of ambiguity is there. See, for example, you imagine that I will ask you to continuously regulate a voltage. What is that? Fan regulator, and I will ask you to make the speed of the fan exactly at a particular speed. Let us say I will ask you to monitor the speed of a fan and make it exactly at some particular speed. Let us say 1000 RPM, something. So what you will do? In your right hand, you will keep the RPM meter, and in your left hand, you are going to continuously change the voltage knob that you have at your home, and you are trying to manage it so that the speed will be constant, irrespective of any disturbance. There may be some wind, there may be some, let us say, fluctuations in the input voltage, whatever may be. I am asking you to keep the speed constant. So what you are going to do, you are going to monitor, and what is the controlling parameter? That is the knob which is there in your left hand. But you assume that, let us say you are a grown-up man or a woman, so you know how to handle that knob, and what you will do, you will handle it so nicely that depending upon your skill set, some person may be very much good at maintaining the speed very close to the desired speed. If it is asked to, if he or she is asked to do at 1000 RPM, maybe 10 or 20 RPM difference will be there. But whereas if I ask the same task to a child, maybe about 10-year-old kid, what he will do, whenever the speed is less, he will rotate it so heavily, that the speed is going to go in that direction. That means he will do nice thing. That means he knows whenever the speed is less, he has to increase the voltage. Whenever the speed is more, he has to reduce the voltage. That means he knows the direction, but he doesn't know the amount which he has to rotate. In that case, what happens? The speed will oscillate either that way or this way. That means what? There is oscillations coming before it actually comes to the actual steady state. Why? Because the fan, which is so having some mass, is an inertial element. So you have to consider the inertia of the fan, and based on the knowledge of the inertia of the fan, usually which will come over a period of time because of your repeated experience with that fan. If I give you that task, it may be easy for you, but for not a newcomer, or for just one human being who has just seen the fan for the first time. The same thing applies for you and for the controller. What is that? So here, the controller has to handle the energies in the inductor and capacitor. Here, that means it is not the actual input voltage change or the output current that is the disturbance. It is because of the energy storage fluctuations, which to meet the new operating point, to handle that, the controller has to be properly designed. That means here, in the last sentence of this slide, I want to highlight only one sentence. Right? Basically, the controller should know the timings. That means it must have in its mind. So suppose if you imagine a controller as a human being, in his mind, the time constants of the machines which he is handling, he should be aware of it. The same thing is applicable here also. The controller should be given the knowledge of timing of the power converter that it is handling. I think this sentence may be more or less suit any controller design. So the controller has to be given a proper information about the timing. That means it must be aware of the time constants. So time constant means what? L by R is the time constant of any inductive circuit. RC is the time constant of any capacitive circuit. That is known thing. That has to be fed to the controller. Then the controller will automatically, that intelligence has to be fed inside the controller. So basically, you are going to whenever I say controller design, what is that? You are going to introduce the knowledge of timing of the power converter to the controller. So then the controller is capable of handling it. So the question is, it is a very what you can say broad sentence which is very difficult to understand. Finally, it has to be implemented. No? So we'll go to the next slide. Here, what is happening? There is just introducing two words for you, which will make we are going to convert that whatever we spoke in English language. We are going to convert that in terms of the terminologies. Whatever I say, the oscillations. Okay. So what is that oscillation? That means whenever the controller is going to handle that change in operating point, how that is able to handle that change, and whether it is going to handle that change after some oscillations, or if at all oscillations is there, how much oscillations, that is what's called as AC analysis. So here you see very good intuitive figures is there. You can see that what is happening in the lower part of the converter, there is a load has come down, and here the load has come down for some value, and after some time the load has gone up. So the load has come down and the load has gone up. So this just what two disturbances have happened here. I was telling you that the disturbance one will be load disturbance, and other will be input voltage disturbance. In this particular slide, I have taken only one disturbance, that is load. So the load has come from high value to low value. This I can consider as one disturbance, and here there is low value has gone from low value to high value. Just see the way the output voltage responds. See, when the load has come down from high value to low value, obviously expect the voltage to go up. But I am expecting the voltage to remain constant. But what is happening here? Not only there is oscillations, but the value which was here at this point, it has shifted. That means the DC value itself has shifted, which is very dangerous. I want the output voltage to be, let us say, 12 volts. It should remain same thing. But unfortunately, what is happening? It is shifting to a new value. Okay. So this kind of shifting which is happening, which is unwarranted, depends upon the DC gain of the converter. Only this thing. That's all. We will proceed to the next slide. We will not spend more time on this one. So, whenever there is a disturbance, we want the output voltage to remain same. But unfortunately, it is not happening here. There is a shift in the output voltage. Okay, there is a shift. I don't want the voltage to go to a new value. I want the voltage to remain same thing. And observe that it is not only going to the new value, and also to settle at the new value, it is taking some time and oscillating. It is taking some time, and during that time, it is oscillating and then coming to a new value, new steady state value, and unfortunately, it is coming to a new steady state value. Okay, it shouldn't have come. That it should have maintained here itself. That means whenever there is a load disturbance, there should have been some oscillations at first. Given oscillation should not be there. Suppose if you have designed excellent control, there may be some more oscillations, and then once again the same steady state operating point. Okay, but here what is happening? There is a shift is there. That shift is because of the determined by the DC gain of the converter. Whereas here there is oscillations. Oscillation is determined by the gain versus phase profile of the converter. So basically, what is the essence of all these things is that whenever I want to overcome the disturbance, I must take care of the DC gain of the overall system. I must take care of the AC gain. So I repeat, it must be taken care. Both AC gain has to be taken care and DC gain has to be taken care. And whenever I say AC gain, obviously one more word I have introduced, because AC, the word itself indicates. So I must also bother about the phase. That's why I have bothered to take care of one more word, that is phase. So in essence, whenever you are saying the control design, what you must keep in mind? You must keep in mind that you have to take care of the DC shift, DC gain and AC gain, and also in the bargain you are going to introduce the knowledge of timing of the power converter within the control. So whatever the control design that we do for any power converter, this is the basic thing that we are going to do. The thing is that how we are going to implement, what are the two preparatory work that is required, that is what is important. There are a lot of preparatory things that you have to do before actually trying to implement a controller. Okay, so but basically this is the thing. Any converter, AC analysis, DC analysis, the DC gain should be as high as possible, so that the shifting is, I don't want shift, but unfortunately the shift is there. So to overcome that shift, I want the DC gain of the loop should be very high. I repeat, the DC gain of the loop should be very high. So that is a little bit contradictory in nature, because if the gain is high, how we can avoid this shift? That is what the control system will do. So at this point of time, let us just keep in our mind that the DC gain should be as high as possible, and AC gain should be according to our profile. That means the knowledge of the power converter should be kept in mind for carrying out the AC analysis. Okay, next. Okay, this some preparatory work is involved. I think already 12:45. Yeah, we just quickly run through these things. What is that? There is some preparatory work that we are supposed to do. We should have a knowledge of 3 filters. Suddenly you will be wondered, till now we were discussing about power converters. Suddenly, why that discussion about the filters? The thing is, in any DC-DC converter which we are going to design, like which we are going to handle in the afternoon session, buck converter and flyback, it is very obvious that it is a DC to DC converter. So there is no question of AC component at output. Okay, and also input, because it is DC-DC converter. Anyway, the input side. But we are interested in only output side. Output side, you cannot expect any AC. So AC has to be bypassed. That means what? Only low frequency has to be, we want to see only low frequency component. That's why all these power converters, since we are using energy storage elements, they are not only for power conversion, they are also for filtering. Okay. So if you take any power converter, you will have L and C. So it is supposed to be a second order filter, filtering all the high frequency components and allowing only the low frequency components to come out. But here, as you just observe, whatever that is being shown here on the slide is an RC filter. You may be asking a question, why we are interested in RC filter? But actually, RC filter is not the one that we are interested. We are interested in LC filter because LC filter is the one that is going to come up on any power converter. Then why you are interested in RC? Because this RC filter is whatever I am showing is a preparatory thing, preparatory slide for this one, which actually we are interested. So this is what we are interested. This is nothing but this is also low pass filter, but this low pass filter is supposed to be active filter, whereas this is a passive filter. Okay, so this passive filter is it will make you prepare for this active filter. Okay, so both will do the same job. What is that? It is going to pass only the low frequency component. But the only thing is that this is very active element, and this is what very important component present in any controller. That's right. So otherwise, we are not interested in this RC filter. Anyway, I have shown one. I was supposed to discuss in detail, but I think let us not spend too much time on this one. So it is a gain plot and phase plot of this RC filter, and you can see that there is a drooping characteristics. Like the gain is going to fall as the frequency increases. Same thing here also. Okay, the gain is falling as the frequency is becoming more and more. Then what is the difference between the previous passive filter and active filter? Here, only thing is that here at this point of time, blindly take this point. Later we can analyze that this is introducing one pole at the zero frequency. Then this is what very important component which will make us go for a high DC gain. That means just now I told you that if you don't want this DC shift, means if you want a very high accuracy steady state error, the DC gain should be very high. Then how you can sure of yourself that the DC gain is high because of keeping the this one particular active filter. So you keep this in mind that this is the one component which we are going to use it in our design of buck converter as well as flyback converter for achieving the high DC gain which you will require to maintain the steady state error. I mean to maintain very less steady state error. That is what? That means voltage regulation. Okay. So this is the RC filter, active RC filter. Next, this one. One more thing, second filter, LC filter. Why this one LC filter? Any power converter, DC converter, this is the must, it will be there. LC filter will be there. And it introduces two poles. It's a 1 by 2 pi root LC is the result frequency. That means it has got two poles at exactly at 1 by 2 pi root LC. Why we are interested in all these things? Because so this is the part of the power converter, and this is the part of the power converter, and we know that this is the place where we are having two poles. So that means this is the information about our power converter which has to be fed to our controller. Just now I was telling you that the position of poles 1 by 2 pi root LC indicates the frequency. That means what? It is giving a knowledge about your power converter which you want to feed it to your controller so that it can handle the dynamic situation properly. So this information is required to feed or you can say to design a controller. Whereas the previous one, that itself is a controller. This is the actual controller. Okay. So these are the three control filters that we are supposed to know. Anyway, this one I just wanted to show you that I will not take more than 3 minutes to brush the basics. Control design, you know that this is the plant, this is the compensator, okay, and we are going to take a part of the output, feed it to the compensator. That is, this is supposed to be the actual controller, and we are going to meet the purpose of maintaining the output voltage regulated, irrespective of disturbances. Okay, so if you go through this simple mathematics, very simple mathematics that has been shown on the slide, you will come to the conclusion that the loop gain has to be as high as possible. Okay, usually there is a confusion for especially for students. Whenever we say open loop gain and closed loop gain, it misleads us in thinking that there are two things. One is when the control system, when there is open loop, one kind of gain. When closed loop, one kind of gain. No, it's not like that. See, we are discussing about closed loop system. But even in closed loop system, we are discussing two terminologies. One is closed loop gain and other is open loop gain. Whenever we say open loop, there is a tendency for us to think that now the control system itself is not there. It's not like that. Actually, most probably, I feel that the terminology should have been different. Like the loop gain is much better word compared to open loop gain. That terminology would have been much better, I feel. Anyway, technically, if you try to understand that, there is nothing like closed loop, open loop. We are discussing about the closed loop only. But the only thing is that we are interested in closed loop gain, but we have to worry about the not open loop gain, loop gain. Let us use the word loop gain. So finally, what is the essence of this particular slide? The essence is that the loop gain should be as high as possible to make the steady state error as less as possible. So loop gain is, what do you mean by loop gain? Just the multiplication of the gains of all the blocks that are present in the loop. So it is a plant is a part of the, in our case, buck converter is a part of the loop. So the transfer function of the plant, then the compensator, it has got some transfer function. So if you multiply all these things put together, whatever you get, the product, the result of the product, that is what is supposed to be called as the loop gain. So let us not go in detail. Finally, our lesson is that the loop gain should be as high as possible. So whatever you design, the controller should have the highest loop gain. Okay. Now we will come to the actual this one, the which we are going to implement. That will be more interesting, I feel. Here, you know that this one is supposed to be the actual power converter. In our case, it's a buck converter or feedback converter. And here, I have please observe that there is a LC filter is there. Okay, so this LC filter is it will be there in any power converter that you take. Okay, so LC filter will have its own resonant frequency, which I will take care. That's what we discussed in the previous slide. Okay, so this is the, you can say the power stage, or you can say the plant. Whatever you can in control terminology, you can say it is a plant, or in our power converter terminology, you can say power stage. Whatever it may be, this one. The terminologies can be different. So this is the power stage. Okay, a part of it. And okay. So a part of the output we are taking and trying to feed it back through an operational amplifier. Okay, this is what I was trying to highlight, that this RC filter, which I showed you, the RC filter, the passive RC filter, and then I showed the little bit upper higher version, that is the active filter. This is what active filter. Okay, of course, this active filter has got several versions are there, and the basic one which I showed you in the previous slide is supposed to be active filter with capacitor in the feedback loop, which is going to provide a very high DC gain. So one problem we can solve, that is the steady state accuracy can be improved. Okay, so this is the one important element which is supposed to be the op-amp with a compensating elements. So usually in the block block representation, you will see that error amplifier will be different and the compensator will be different. So that is one more place where usually the misleading will happen, right? So here you can see that error amplifier is there, as though there is reference is there and the actual is voltage is coming here, that is feedback voltage, and there's error, and the error is fed through a compensator, that is a PI controller. But in practice, please think that they are combined. You can never imagine, you cannot imagine these two blocks to be separate. They are integrated. Whenever I say I think the more good word should be compensated error amplifier, maybe more apt word than compensator and error amplifier. We cannot separate it. But for better understanding, usually in the textbooks, what we do, we separate it. Error amplifier is separate and compensator is separate, as though they are physically separate. But actually, they are not physically separate. Suppose if you take an operational amplifier and build compensating components around it, and then it will do the function of both the generating the error as well as compensating the error. Both will be done by the same block. So this is one more place where people will, students will get confused. So whenever we are trying to guide our final year projects, students, I think these things has to be properly handled. For the students has to be taught properly. These blocks, whatever the confusion that is there, they can be resolved, and this whatever they have studied in the third year of this one control system, they will be brought back to their memory. Okay, so basically There are some LC filter is there, then actual power converter is there, and then op amp that is with compensator is there, and the voltage divider is there. Okay, because you cannot directly bring the voltage, output voltage will be very high, but whereas your signal level electronics will be low voltage electronics. So it has to be stepped down through using some sensors or voltage divider network. So basically, what I want to say is that there are different, majorly voltage divider network is there, LC filter network is there, power converter is there, then a composite error amplifier is there. These things has to be properly transferred in terms of transfer functions, so that we can teach the controller a proper lesson in trying to handle the dynamics. That's all. That is the essence. Okay. Here, just there are a couple of slides are there. It's basically for deriving the transfer functions. This one such pulse width modulator. What it will do? It will take the control signal as the input, and it will output the PWM pulses. Okay. So there is obviously there is a sawtooth, and we are going to compare with a control signal, and the output volt will be a PWM pulse. Okay. So this one. So finally, the transfer function is 1 by P ramp. Whatever the ramp voltage is there, this one. All these things are just the explanation for what is the transfer function of these different blocks. That's all. Because finally, we want to handle them mathematically to get a proper value of the P and I in a PIA controller or PID in a PID controller. That's all. To arrive at those, we need all these things. Other than that, the necessity is not there. Okay. Now, actual plan. That means what? It will be now in our discussion. We are going to handle buck and fly. Right. So what I have done in the left hand side, I have shown you the buck, and in the right hand side, I have shown you the buck boost. Why I have shown you buck boost? Because we are going to handle the flyback, which is nothing but the isolated version of the buck boost converter. So you see that how many transfer functions have listed on the this one board. You can see here plant transfer function, that is here. Duty cycle. Okay, that means exactly how you can control the transfer buck or buck boost through the duty cycle. So the output voltage with respect to duty cycle, this particular transfer function will give you the output voltage, how the output voltage will vary according to the different frequency components of the duty cycle. That is what this transfer function will give. Of course, don't worry about the second one. It is just a different way of writing. That's all. And similarly, what is that? This one line transfer function say how the output voltage will vary with respect to the input voltage disturbance. That means basically one transfer function is giving you a picture how to control. First one will give you an idea how to control the power converter. The second one is giving the idea how a disturbance is controlling. Okay, you must have an idea that how a disturbance is controlling your converter. So then only you can have an idea how your duty cycle, which is the controlling parameter, has to control the power converter. So these are the two things which is very important because we anticipate a lot of line voltage disturbances. So these are the two things that are there, and the same thing has been repeated for buck boost converter also here. Okay. So here this is a standard this one feedback stage transfer function. Any power converter you take, you can see this kind of diagram. Okay, where you will see the reference voltage in the non-inverting input, and you will see this every power converter has got a negative feedback. You can see in the negative input, that is inverting input, you can see the actual signal entering. That means the step down signal is entering the negative feedback, and the reference voltage is giving the positive feedback. So this is a standard operational amplifier circuit which complete, that means PI, PID, PI, whatever you want to implement. This is the basic thing. Okay, so I think we have sufficient discussions that has happened in the past 3 days regarding the implementation of this one. Only thing is that I want to bring your attention the fact that just see the importance of the op amp that you have discussed in the past 3 days. How important this one in the design of the power converter. Actually, what I can say is this is the heart of any power converter, because this is a control system. Mainly this depends upon any analog control of any power converter, depends completely on this particular op amp circuit. Okay, so complete understanding of this op-amp circuit along with its transfer function, the behavior, input impedance, output impedance, all these things, how the frequency response, everything about this one op-amp is so important, which will make you design the complete system, feedback loop system for a power converter. Okay, so already the sessions that you have attended in the previous 2 days will definitely help you to have a thorough understanding of this one. So here in this particular session, it's only to highlight the importance of this one. That's all. Okay, in the context of power converter design. Now finally we are ready to close the loop. Okay, so this is one thing I want to spend a little bit more time. Shankar, till what time will we do? 1:30 or 1:15?
Sir, you can take 10 more minutes, sir.
Okay. Okay, 10 more, 15, 10 minutes I'll take. So here what we are doing, we are going to design the control. Okay. Finally, our aim is to design a closed loop controller. We are very much accustomed with this one. We are seeing since third semester onwards, we are able to see this particular what is that expression. So finally, in a nutshell, what I can say is that if you think that this is a closed loop transfer function and concentrate only on the denominator, and you can see that whenever the denominator becomes 0, you can say 1 over 0 is infinity. What will happen? It will explode. That means your system will explode if the denominator becomes 0. So when the denominator can become 0, then g of s into h of s becomes -1. So this is the crux of the entire control system problem. Okay. So g of s into h of s, if it becomes -1, our system is going to get destroyed. It will explode. So we have to avoid this situation. This gives an insight to that how to avoid this one. So in the context of terminology, what we'll say, we want to avoid the loop transfer function. This is what I'm saying. Actually it is a closed loop system, but I am concentrating only on the loop transfer function. So if g of s is the plant transfer function and h of s is the loop transfer, feedback, if you multiply, that is what is called loop transfer function. And if it should, I don't want its magnitude to be 1, and I don't want its phase to be 180 degrees. Why? Because minus. See, usually minus means what? It should be the vector is rotating by 180 degree. Okay. So what is happening? The gain is becoming -1 means what? I don't want the argument to be 180 degrees. I don't want the argument to be 180 degrees. Okay. I don't want the magnitude to be 1. These two, if it coincides, I am in danger. I want to avoid at any cost. So technically, what I want to convert this in the English language, if I have to utter this sentence, I should say that at the crossover frequency, that means what? Where the gain is 1. I don't want my phase to be equal to 180 degrees. It's not even 180 degrees. I don't even want to be near to it, because any danger, it is not just we have to be away from the danger. We should sufficiently away, because even small changes may lead us to instability. So sufficient distance we have to maintain from danger. So the danger point is that the gain should be equal to 1, and the phase, if it becomes 180 degrees, we are in danger. So we should be sufficiently away from the danger point, which is called phase margin. So phase margin is very much essential to keep away from the danger point of magnet becoming 1. And so all the control system design is, in a nutshell, is how to be away from this one, keeping all the other parameters like the design overshoot, then undershoot, steady state accuracy. You have to maintain all those things. But first of all, you have to be very much sure of this danger. First, if your life is saved, then only you can do many other things. So you should be away from this point, and then once you are assured that you have a sufficient phase margin, then you can do other things of improving your steady state accuracy, improving your all those things. So there are some what is that? A couple of diagrams that has been written here. That means purely sees these different oscillations. There are a lot of oscillations are there. If you, as the phase margin is more and more, you can see a lot of oscillations is there. Basically, this slide is giving you a picture that your phase margin should be as high as possible. If it is low, you can expect oscillations, and if it is very low, what happens? You can expect the danger point. You are very near to danger point, and at any moment, small disturbance also, it might lead to instability. Okay, we will not go in detail this one. There are some criteria are there which we are going to take up. These are the criteria that you have to handle. You have to look into in taking care of any control system. Okay? That means you should know. Basically, these parameters are making you understand how the loop transfer function. Suppose if you plot a loop transfer function and visualize the diagram, how it should look like for a stable operating system under the umbrella of which you have to work, and also to improve the steady state accuracy, to reduce the oscillations and to control the frequency of oscillations. These are the rough can say criteria which you have to follow, because the control system is so difficult in the sense that many factors have to be taken care. Usually people will resort to what is the iterative procedure, because iterative procedure is also difficult. Control system design is also difficult. So actually, what I feel that there should be a perfect you can say mixture of both iterative procedure as well as, and to aid the iterative procedure, a lot of theoretical concept should be fed to any student so that he can take care of those iterative things in a nice way. Okay, so here I have shown you that a bad feedback stage transfer function where the criteria has not been met in the left side, and in the right hand side you can see the criteria has been met by the proper design of the op-amp. So all this criteria has been taken care in the model plot that has been shown on the right side. It is supposed to be recommended, and it is not recommended. Basically, this is the comparison. Okay, and here, so this is one. I just want to conclude this presentation with this last type 3 compensator, where you can see that type 3 compensator is supposed to be you can say PID, everything is there here. Okay, but in many even I was last year I was I met one Boeing flight design engineer. He was saying that even the latest flight controller that Boeing aircraft company is using, even now it uses PI control. Even though we are saying that for artificial intelligence, fuzzy logic, neural network, everything is important. But having said this one, even very complicated mechanism like a flight controller is still managed by a basic PI controller. So that's what he was saying. Just when I met him in the last year itself. So at the present situation is also the PI control is dominating the 85% of the control system that are there on the working on this system. I mean on this earth. Okay. So having said this one, this is the diagram of a type 3 compensator. So this one, whatever it is shown, you can see that 100% PID can be implemented, and whatever that is shaded portions are there. Here, left hand side, it is indicated what exactly this one. The shade portion indicates the kind of poles and zeros that these things are incorporating. Okay. Basically, this type 3 compensator is incorporating many things. Okay, so these how to incorporate this? What are the values of these things? That is what the design. Why I took the control system design more in detail, because as far as the power converter design is concerned, if you just calculate L and C, maybe you are sufficiently in a good position to handle. But whereas the control system, there are a couple of components. If you just count physically, how much is there? 1, 2, 3, 4, 5, 6 components are there. But these 6 components will make our life so troublesome that we may spend weeks together time in tuning a PA controller. So here there are some couple of theoretical things that are there to guide us in selecting the proper values of these things, so that we can have a proper stable power supply. Okay, I think I just show you this one. These are things that we are going to discuss in the afternoon. One is the closed loop buck converter, and other is the closed loop feedback converter. We'll try to implement these two in the afternoon and try to see whether the analysis can be done. Anyway, we will build this one. We have to build text. All these things have been taken care because we are used to Tina. So this last slide, I think we can skip it. So in the analysis, we are going to do this one. So I'm going to end the presentation now. Any questions are there? We can take.
Participants can interact with the resource person. If you have any doubts or clarity is needed, you can unmute yourself and talk.
I think if no one is there, I think we can wind up the session.
Okay, so thank you very much, sir, Dr. DrAnanthaPadmanabha, for such a wonderful presentation on bug converter, flyback converter, and associated control system design. Dear participants, we'll be restarting the afternoon session at 2:15. So please join back and at 2:15. We'll be discussing about the hands-on session, how to implement the same controllers and DC to DC converter, whatever we have discussed in TINA software, and the analysis of the results. Thank you once again, sir. Thank you very much.
Thank you, Dr.